Today we shall take a look at a summary explanation and example of an atom within a quantum computer and its significance. But first, we shall get clarity on the brief meaning of computing, quantum, bits and qubit, an atom, classical computers, quantum computer. At the end of this session, we shall also be learning how uniquely a quantum computer outperforms computations that would be practically impossible for classical computers. Computing is the act of calculating something, adding it up, multiplying it, or doing more complex math functions to it. Computers are named for this process because they can compute faster than most people. What is a quantum? To a layman, a quantum, plural, quanta, is the smallest discrete unit of a phenomenon or event. For example, a quantum of light is a photon, and a quantum of electricity is an electron. Quantum comes from Latin. In physics, a quantum is the minimum amount of any physical entity involved in an interaction, meaning the hypothesis of quantization. A classical bit can be either 0 or 1. A quantum bit, or qubit, is a superposition of 0 and 1. A single qubit therefore takes two classical values at once. Every operation on the qubit is done on both values at once. You need an infinite amount of bits to describe the state of a single qubit. An atom is a particle that consists of a nucleus of protons, and generally neutrons, surrounded by an electromagnetically bound swarm of electrons. Classical computing is another name for binary computing. In this traditional approach to computing, information is stored in bits that are represented logically by either a 0, off, or a 1, on. Today's processors, including x86 and ARM processors, support classical computing. Classical computing contrasts with quantum computing, a type of non-classical computing that represents data in quantum bits, qubits. A classical bit is either on or off, but a qubit can be on and off at the same time, a condition known as superposition. Unlike classical computers, quantum computers require specialized and expensive infrastructure. They must operate at near absolute zero temperatures and be shielded from outside radio waves, light and magnetic fields to prevent errors. So, how uniquely a quantum computer outperforms computations that would be practically impossible for classical computers. In the context of quantum computing, an atom typically refers to a qubit, which is the quantum analog of a classical bit. Quantum computers process information using quantum bits or qubits, which can exist in multiple states simultaneously, thanks to the principles of superposition and entanglement in quantum mechanics. Here's a professional definition, explanation, and an example of an atom, qubit, within a quantum computer, along with its significance. Definition. In quantum computing, an atom refers to a quantum bit, or qubit, which is the fundamental unit of quantum information. Unlike classical bits, which can only exist in a state of 0 or 1, qubits can exist in a superposition of both 0 and 1 simultaneously, greatly expanding the computational possibilities. Explanation. A qubit in a quantum computer, an atom, is typically implemented using physical systems, such as atoms, ions, or superconducting circuits. For example, in a superconducting quantum processor, a superconducting circuit may act as a qubit, and its quantum properties are harnessed for information processing. The quantum state of a qubit can be manipulated through quantum gates, allowing for the creation of complex quantum circuits. Importantly, qubits can also be entangled, meaning the state of one qubit is dependent on the state of another, even if they are physically separated. This entanglement property enables quantum computers to perform certain calculations more efficiently than classical computers. Example. Consider a quantum computer with qubits implemented using individual atoms. These atoms can exist in a superposition of states, representing both 0 and 1 at the same time. Quantum gates can then manipulate the quantum state of these atoms, allowing for the creation of quantum circuits. Additionally, entanglement between atoms allows for correlations that classical systems cannot achieve. For instance, if two entangled qubits are measured, the state of one qubit instantaneously determines the state of the other, regardless of the distance between them. This phenomenon has significant implications for quantum communication and quantum information processing. Significance. The significance of the quantum atom, qubit, lies in its ability to represent and process information in ways that classical bits cannot. The principles of superposition and entanglement give quantum computers the potential to solve certain problems exponentially faster than classical computers. Quantum computers are particularly promising for tasks such as factoring large numbers, simulating quantum systems, and optimizing complex systems, which have practical applications in cryptography, material science, and optimization problems, respectively. Before we summarize, the intersection of artificial intelligence, AI, and quantum computing is an exciting and evolving field that holds the potential to significantly impact the way we approach complex problem solving. Here are some key aspects of the relationship between AI and quantum computing. Speeding up AI algorithms, quantum machine learning, QML. Enhanced optimization with quantum annealing. Handling quantum data in AI. Quantum neural networks. Secure AI with quantum cryptography. In summary, the integration of AI and quantum computing has the potential to bring about transformative changes, from speeding up traditional AI algorithms to enabling entirely new approaches to problem solving in the quantum realm. As both fields continue to advance, we can expect further synergies and innovations at the intersection of AI and quantum computing. In summary, the quantum atom, qubit, is a foundational element of quantum computing, and its unique properties enable quantum computers to perform computations that would be practically impossible for classical computing